Greetings fellow space explorers and welcome back to the channel. Today, we will be providing an in-depth overview into some of the most perplexing mysteries surrounding the birth, evolution, and ultimate fate of our universe. From the first moments after the Big Bang, to the structure of the cosmos we observe today, this will be a journey across many of the great frontiers of modern cosmology. First, let's rewind the cosmic clock back to the very beginning. The most widely accepted theory for the origin of the universe is that it began approximately 13.8 billion years ago, from an initial singularity known as the Big Bang. In just a sliver of a second, space and time emerged and all the energy and matter comprising the observable universe today exploded into being. But what exactly happened in the moments immediately preceding this? One theory suggests that before the Big Bang, the universe was actually contracting, after initially expanding from a prior Big Bang event. As it contracted, quantum fluctuations caused it to spontaneously begin expanding again, leading to our current Big Bang. Essentially, the history of the universe may be cyclical in nature, oscillating between expansion and contraction phases over the course of eons. Now, once the expansion from our Big Bang began, the earliest moments involved unfathomably high energies and densities. In a fraction of a nanosecond, the first elementary particles like quarks emerged from a searing primordial soup of unbound energy. These particles soon coalesced into protons and neutrons as the universe cooled. Just after the Big Bang, an even more mysterious and important phase occurred, which shapes the universe we see today, cosmic inflation. Lasting nearly 10 to the power of 32 seconds, the entire universe ballooned in scale by at least a factor of 10 to the power of 78. This brief epoch of hyper-expansion smoothed out the distribution of matter and flattened any curvature in space-time. Without inflation, the universe would have collapsed quickly or displayed far more irregular, large-scale structures. What mechanism caused inflation? The leading theory proposes the hypothetical inflaton field, driving this exponential expansion through a vacuum energy density. As inflation ended, the decay of the inflaton field led to a phase transition that filled the universe with the hot dense particle soup of the early universe. Detecting the gravitational wave signals from inflation remains a major goal in cosmology today, as it would offer insights into physics at energies 1 trillion times above what is achievable in the largest particle accelerators. In the first 3 minutes after the Big Bang, nuclei heavier than hydrogen like helium and lithium formed through nuclear fusion as things cooled rapidly. After around 380,000 years, the universe finally cooled enough for electrons to bond with nuclei and form stable atoms. The universe became transparent to light as photons decoupled from matter. Today, we detect this relic light pattern in the cosmic microwave background radiation. Let's now talk about some of the deep mysteries confronting our understanding of how cosmic structures, like galaxies and galactic clusters, formed and evolved following the Big Bang. One major unanswered question is how the very first stars, the so-called population 3 stars, were able to form just a few hundred million years after the Big Bang. Models suggest they may have been 100 times more massive than the Sun, fueled by primordial hydrogen and helium. Current simulations cannot fully explain how they coalesced so rapidly after the Big Bang. Equally puzzling are the supermassive black holes, detected from 1 billion years after the Big Bang. They are estimated to range from millions to billions of solar masses. How could they have formed and grown to such enormous sizes in such a relatively brief period, when galaxy formation was still in its infancy? Their origins remain unclear. Understanding the full chronology of cosmic reionization is another key area of research. The earliest generations of stars and galaxies provided the ultraviolet radiation that gradually reionized the primordial neutral hydrogen in deep space. But gaps remain in mapping out precisely when this phase transition occurred that produced the ionized intergalactic medium we see today. A persistent mystery in physics is the constituent nature of dark matter, which comprises of 85% of all matter content and 1/4 of the universe's total energy density. Leading candidates like weakly interacting massive particles or WIMPs and axions continue to elude detection. And theories proposing dark matter is composed of macroscopic objects, like primordial black holes, must contend with a variety of constraints. Dark matter remains shifty and imperceptible, for now. An even more perplexing phenomenon is dark energy, which drives the observed accelerating expansion of the universe, first discovered in the 1990s. This mysterious vacuum energy accounts for a whopping 68% of the total energy density in the cosmos. But its origins, composition, and even fundamental nature remain unknown despite its overwhelming preponderance. Is it truly a form of energy intrinsic to empty space, or could it signal some breakdown of general relativity on cosmic scales? Insights into dark energy's properties may require a revolution in physics. Some speculate our universe may not be all that exists, and that other, bubble, universes may exist beyond our observable cosmic horizon, separated by inflating space. Proponents of a multiverse theory argue that fundamental physical constants like the Higgs vacuum value we observe may be due to chance, with differing values realized across universes. However, the multiverse concept remains firmly in the speculative realm, for now. Looking ahead billions of years from now, one scenario predicts continued cosmic expansion until the galaxies accelerate beyond detection range. With star formation ending, as matter exhausts, black holes gradually evaporate away through Hawking radiation, over unimaginable timespans. The ultimate fate may be heat death, where the universe becomes a sparse, uniformly cold void. But other projections suggest cosmic acceleration may reverse, leading to contraction and a big crunch similar to the Big Bang in reverse. Or perhaps vacuum decay will trigger a phase transition, spontaneously generating a new vacuum with different properties. The ultimate destiny of our universe still awaits revelation. Now, let's transition to discussing some of the most extreme and mysterious phenomena studied in astrophysics today. Neutron stars are essentially stellar corpses, the ultra-dense remnants of massive stars that ended their lives in supernova explosions. Just a teaspoon of neutron star material would weigh 1 billion tons on Earth thanks to the incredible gravitational crush. When two neutron stars collide, they generate energetic bursts of gravitational waves along with electromagnetic radiation. Analyzing the aftermath of such merger events provides insights into the nature of gravity and extreme matter. Scientists also suspect that such mergers likely forge heavy elements through rapid neutron capture, or the R process, scattering this material across space. At the center of galaxies reside supermassive black holes containing millions to billions of solar masses condensed into tiny volumes. They anchor galactic ecosystems, glowing brightly as enveloping matter accelerates and radiates before crossing the event horizon point of no return. Relativistic jets spew from their poles as matter twists in their vice-like gravitational grip. Unraveling the growth of supermassive black holes across cosmic time remains an area of intense research. And then there are the incredibly luminous quasars that shone as some of the brightest objects in the early universe. These active galactic nuclei are believed to be powered by rapidly accreting supermassive black holes. Quasar luminosity provides a means of studying the intergalactic medium along the line of sight, by analyzing the absorption of light at key wavelengths. Distant quasars thereby offer glimpses into galaxies and cosmic evolution billions of light-years away. Well, that concludes our cosmic tour through some of the biggest mysteries concerning the birth, evolution, contents, and fate of our expanding universe. From cosmic inflation to dark energy, quasars to neutron stars, the frontiers of cosmology and astrophysics continue pushing outward to unravel nature's best-kept secrets. Yet for each riddle we solve, new and deeper questions arise as our knowledge expands. The quest to understand our cosmic origins shows no signs of ending, over 13 billion years since it all began in a fiery flash. The universe beckons endlessly. Our journey to understand it has only just begun. Thanks for watching.